So today we're talking about principal components, which is actually something in chapter 17 on multivariate methods for describing data. We're picking up homework today. The student presentation, John Ching is going to do that on Monday. We have a couple midterms and with the homework due, so it seems reasonable to do it on Monday. So we'll present kind of a little more in depth on one of the data examples. The next presentation after that, Courtney would be up, and she'll probably do that back on the next Friday related to topics. So that's what's going on. So today we're talking about multivariate things. And the reason for doing this now, rather than kind of just going through the book order, is when you're dealing with regression, you often have a situation where you have a bunch of x variables, and some of them can be highly correlated with one another, right? Or not perfectly correlated, but reasonably high. And if you have a bunch of variables, they can be related to kind of the same underlying topic. So size variables can all be pretty highly correlated if it's measurement on, hospital size, all these different things have to go together, school size, all these different things go together, counties and population concentrations and things all go together. So if you try to use them all in regression together as predictors, the regression does things that can be kind of funny. Right? That because of that high correlation, you can get some results that seem counterintuitive, seem non-significant, when you're sure that there is a relationship. And one way of dealing with that is to try to narrow it down to a smaller group of variables or average them, or maybe use principal components. So it's kind of one way of looking at the data, one way of trying to summarize it and get it down to a smaller group of predictors, and it has its own uses. Right? But this is in the general section of multivariate statistics, that you might have many variables and you want to summarize the overall pattern. So principal components, or principal components analysis, PCA, could be one part. There is canonical correlation. Mostly I've seen this in social sciences. We have a bunch of measurements of one factor and a bunch of measurements of another factor, and you want to know how these two things relate to one another. So you might look at the correlations between sets of variables. If you're trying to use a bunch of variables to distinguish between two groups and separate two groups, there's discriminant analysis, which looks at ways to predict which group people are in. We will also do this with logistic regression. We will talk about that in more detail in a later chapter, to predict membership in one group versus another. There's general cluster analysis, techniques for finding groups in data, and so on. These things are kind of mentioned quickly in that chapter. We're going to talk about more principal components as a way to look at multivariate data. I'm not spending as much time on some of these things. We will come back to logistic regression. But the discriminant analysis or cluster analysis or canonical correlation, if one of those topics from looking at the chapter particularly looks interesting to you or has some relevance to some work you're doing or a paper you're reading for another class, could be the basis of a project. Right? There could be other resources beyond our book that would go into those in more detail. There's things in R for doing the computation, so you could learn that, and so on. But we're going to look at the principal components. Right? So in this, you have your Y outcome, and we have a bunch of predictors. Right? X of p minus 1, something like that. And if some of the x's are highly correlated, then the standard error for estimated regression coefficients can be quite large. The technical reason that this happens in terms of the math and the computation, computing the least squares estimates, is there's some need to take the inverse of a matrix. And then the design matrix that sets up all the predictors, that inverse thing that you take can be quite unstable. It can be nearly perfectly singular, which means not invertible. Right? And so just as a more basic kind of explanation of that, say x1 is temperature in degrees Celsius, and you've converted it to temperature in degrees Fahrenheit as well. Well, x2 is going to be 32 plus 9/5 times x1, so there's a perfect linear relationship, right? And so if you're ever trying to model y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus some error, any change in beta 1 you would want to make, right, could be matched by a change in beta 2, and you get exactly the same relationship. Right? If you increase beta 1 by 1 degree, right, that would suggest that x2, to kind of make the compensation, would come down by a certain amount. Y maybe is something like productivity of some type of crop, some measurement of output, right, related to temperature. And if you have both measurements of temperature in there, it's just not going to make any sense. And there'll be an arbitrary change in these coefficients, and the estimated coefficients, and you won't be able to tell what the values are. They could go from negative infinity to positive infinity, change the other one, and it would fit. Right? Now, if it's not even, that would be extreme, and it would be kind of ridiculous to put exactly the same variable in there twice, right? And R wouldn't even compute it. It would say these things are perfectly linearly related, and it will just give you an error. So it can't do it. Right? The standard error is going to be really big. But say you had two different measurements. x1 is degrees Celsius at 6 a.m. and x2 is degrees Celsius at 9 a.m. Well, those two are going to be so highly correlated that, again, you could run into this problem. They won't be perfectly correlated. They might have a correlation of 0.99, something like that. And so, again, you could basically trade off one for the other in an arbitrary way. Increase one by 1 degree, increase the coefficient by 1, decrease this coefficient by 1, and basically you get the same prediction. And so it just can't tell, and numerically that comes up. Right? So instead of using a whole big group of predictors, right, you could choose one. Right? You could choose a representative one. Right? You might do something, like you might just choose 6 a.m. Let's use the 6 a.m. version. Or 9 a.m. versions if you don't want to get up so early. Right? And just do one of them. Alternatively, you could average them if that makes sense in the context to take averages. Right? And so the average temperature between these two might be better predictor of productivity of somehow. Right? So you can choose one predictor, right, or a small set of predictors from a big set. So that you eliminate a lot of the redundancy. So you kind of have one thing that does each dimension and try to pick things that then capture most of the variability in the x's, but are uncorrelated with each other, or less correlated with each other. Right? You can maybe average some predictors together, if that makes sense. Sometimes you could take one predictor and maybe take differences, and then you get kind of a different dimension that's kind of less correlated with it, right? So you could kind of choose one predictor, and then the second predictor you use, is a difference versus the first one. Right? So if you're trying to predict something about a health outcome, maybe you have weight or some physical characteristic at baseline. Right? And then you're looking at time, measurement again, a couple weeks later or a couple months later. Well, instead of using that same exact thing, maybe you look at difference. And so the differences going up and down might be relatively uncorrelated with the baseline measurement, even if the two are kind of, something like that. Or you use a technique like principal components. Can be used to kind of choose a new combination of variables in some way, right? And so what are these principal components? So the principal components, create new variables from that. So if you have a bunch of variables, x1, x2, x p minus 1 that you might have, or let's say xq, as a set of variables, right? We're going to look for linear combinations that are sums of these things, xi's, right? And so this is a linear combination of x's. And these things get, right? So this could be an average, could be a difference of two, could be selecting a particular one depending on how you set these multipliers in there. And the way principal components does is it essentially looks at the eigenvectors and the eigenvalues in the space of the x dimensions. So if you had linear algebra, it uses some techniques there. Right? So if you had two x values, x1 and x2, right? And you had kind of their scatter plot of points, and they might be related, right? Somehow. Right? We're going to choose the values of c to combine those two to get the longest dimension along that there. Right? And each point is going to be projected down to this dimension here, and so we'll get the new points along that dimension. The center, and so they're going to have scores along that. Right? The other thing that gets done, right, that'd be a first principal component that gives the maximum distance from combining two. Right? The second principal component goes in, is another combination like this, but it's chosen to be, so if this is the first one, it's chosen to be perpendicular to the other one, so uncorrelated with it. So it's chosen to go this direction, and then all of these points are projected onto here, and they get some quantitative score based on combining those. Right? So the first principal component takes the longest dimension, right? There, the second one, and so there's ways of finding those. And they're related to the eigenvalues and eigenvector spaces for the x space that's there, right? And so that numerical technique gives you these other variables, and then we look at how the variables get defined. Sometimes the coefficient c will kind of imply that we want to average variables together. So maybe I'll just take the average of them, and that's our first one. Sometimes they will take a group of variables, add them together, and the coefficients will be negative on another group of variables. So it's kind of a difference between sets of variables. And if you usually choose a small number of principal components, 1, 2, 3, or so, to represent a larger dimensional space. So if this is 20 variables, maybe you can get by with 2 or 3 principal components and use up the variability. Right? By variability, I mean that the variance of one of these linear combinations, right, is, there's a sum, so it's the variance, let me write what L is, that linear combination. It's, oops, I wanted to write it inside, is the variance of the sum of the CI's times XI's. So this can be written as, there's a CI squared times the variance of that variable plus there's a 2 times the sum of the covariances of xi and say xk if you take the 2 different variables. So this is kind of a sum of variances with these multipliers things there. And so the total space has a certain determinant, that's the total total volume encompassed by those variables. So there's a total variance, and part of it in the first principal component is going to be hopefully a large percentage of the total variability spanned by the x's. If you get 2 variables, like in these pictures, that are highly correlated, well, most of the spread is really taken up in that longest dimension. But if you had 20 variables, maybe you could get one that takes up a lot of the space and spreads out the values, and then another dimension also spreads out a lot of the variance. And so you can get by expressing most of the variability in this lower dimensional space. So multivariate kind of does neat stuff like that. Right? But you get these new variables. You estimate the C's based on the eigenvalues and eigenvectors and making things perpendicular. And then you get new variables, and then you can put those into the regression and try to interpret what they mean. So let's look at some examples of this, right, of what it does. So the handout's a little bit longer, it's a little more intensive in terms of output. Also, I kind of went overboard a little bit in some examples. And we're going to discuss a number of examples. There's a couple examples from the book. The first is an example, and I designed an experiment where there's 11 measurements on each rod, so there's kind of 11 repeated measures. And so these 11 are highly correlated, so you probably don't want to put all of them in there to predict at once. The second example, that doesn't work so well. The second example that's in the second case study, more of a social science study where they have 30 couples, and then there's 4 measurements from the husband, 4 measurements from the wife. And so there's these 8 measurements about their relationship. And so using all 8 is a little bit noisy, so maybe there's a couple key factors that can be brought out of this that are combinations of those measurements. We're going to start with a classic macroeconomic data set where there's some highly collinear regressions, and then look at some other ones. So there's a data set in R, it's one of the basic ones called Longley, and if, I'm going to have to put this over here, make this bigger so it shows up, and it's a bunch of macroeconomic variables over different years. Right? I know that's kind of small. But we do things like try to predict employment. Here's employment. So this is the employment variable on the y-axis of these, and I know it's kind of small, right? But what you can see is a bunch of these have pretty high correlations, right, to that. There's GNP, so gross national product. There's a GNP deflator, so it's kind of a relative scale measure. Number of people who are unemployed, number in the armed forces, population size in year. And so many of these are pretty highly correlated to that. Armed forces during this time period is changing, so it's a little bit less correlated with it, and then unemployed are. But many of these others are. particularly G and P, that's extremely strong, right? But, there's kind of the rationale that all these things could be related to employment levels. If you run the regression, though, of employment on these other variables, look what you get here. You do get a high R squared. It's almost perfect prediction. But the coefficient for G and P is not significant. The coefficient for G and P deflator is not significant. Population-related unemployment is not significant. Right? Now, this is multiple regression, so it's not significant given the other things that are in there. Right? But it just seems to not make much sense because we see these super strong relationships. So we know that it's related, but why does this happen? Right? If you just regress on G and P by itself, for instance, you do get a highly significant regression, and it's 0.967 R squared. That's what we would expect. So what happens when we put all these other variables in there? Well, there's one measurement of, I didn't copy all those out. Didn't copy those in there, but there's something called a variance inflation factor in regression. And you can compute this on a set of X variables. And large values of the VIF, say VIF over 10, tend to alert you that there could be a collinearity among these variables. Right? And it might not be a collinearity just between two of them. There might be 3 or 4 variables that are quite similarly related. So there's some linear combination or between multiple variables that tends to be extremely correlated. Right? And there's this package called TLR. If you run that, you get those. I thought I had saved those values in there. But in any case, those end up being like in the thousands, right? Extremely high, right? Higher than you typically would see for differentiation. And so it suggests that exactly what you're seeing over here in these plots of many of these X variables, there's also these high correlations. If you just look at the correlation of the different, the other thing we could do in that, you could look at the correlation of the Longley variables. Let's round everything to a couple decimal places. Right? That many of these GNP deflator, population, year, many of these things are extremely correlated with each other. So putting them separately in the, all together in the regression, you can kind of arbitrarily trade off some coefficients and still get the same fit. So you can't really determine where they are. And that's related to the reason that some things that we know that individually would be predictive and significant show up with p-values that are not. Because it just takes the best of the best and kind of disregards the others. And so it's not very satisfying to do this regression with all these things. It makes it hard also to do automatic step selection because you could end up with a variable and excluding some, but again, it's not related. Right? So you might do principal components. There's a principal components command in R, and you just put in all your different X variables here that you might like to use. You can do it on the original variables or kind of standardized variables. You can do it in terms of the covariance or the correlation. Right? If the X variables have very different scales, you can end up, and you don't do it on correlation, you could end up picking the variable that's just measured with a wider scale. So there's something kind of desirable about doing it on the correlation scale, but really you should really pay attention to how it goes in terms of is it meaningful. And this one says it to keep the principal component scores that would come out of that. Right? So if we run that, we get this summary of things, and it will show us something about 6 principal components. There were 6 variables in there. And one thing it gives is the proportion of variance associated with that one dimension. And in this case, between these 6 variables, about 77% of the variance in the space of the x's seems to be just in one direction, right? With all these things that are super highly correlated, related to year and just time going forward and the population growing in the United States, that kind of change in size over years is going to be the dominant factor. And then there's a second one that's about almost 20%, and then the other dimensions are kind of residuals off that are quite less important. So this would suggest by taking the first two principal components, you can get about all the information in the X space that's available from all six. So you can reduce from 6 down to 2. The loadings is a term for how these things get multiplied on there. Right? And as it's done here, it's not exactly standardized, but these are the 6 variables, and these are the multipliers that would go onto them. Right? And they're all positive. Right? They are kind of quite similar for things that are highly correlated with a little bit of difference. So this is almost like an average, right, of those, right? The second one, right, has armed forces and unemployment, right? There's a positive and a negative in there, right? So it's kind of a difference of those. And so the first is like telling you that the first one's kind of like an average of all these different things, and the second one is kind of like an interesting contrast between the number of people in the armed forces and the number who are unemployed, right? So if you want to average all those, excluding the first, the last one is our employed, this thing will compute the averages by year of all those variables, and this will do kind of a difference of those two things. So this would suggest that if you regress employed on the average and then this difference between these two factors, you would get, a decent regression that would, that's how it would be used, right? It would suggest 2 new variables in place of all 6. So this would be the estimated coefficient. This one only gets an R² of 0.84. Before we were dealing with like 0.99, and we know that G of P by itself is a little bit, is higher than that. If you wanted to try to use these 2 variables like that, principal components would suggest you take something like an average and something like this contrast to put in there. And then these are, well, the first one is significant and this difference is not, but anyway. The things that are in this principal components in the Lockley data is there are different scores. So there's a score on principal component 1, principal component 2, and so on. Right, that's in there. You could regress on the scores themselves. Right? That gets a little higher R². The meaning of the score is exactly, it's kind of this interesting combination of things. The book and other sources make a point that it's hard to use exactly that principal component in a regression. I mean, if you do, it has certain coefficients on there, right? For somebody else to do that in a new context, they have to use, right, those exact coefficients. So it's not going to work quite as well. Or they won't be able to reproduce it. They'd have to. This is the plot of those couple first components. There's only 16, so it's kind of smaller, right? Is there kind of a thing? Yeah.
Can you hear it?
I can kind of.
Kind of. It's very loud.
Is it very loud? So.
Super loud.
It's the janitor.
The janitor?
She heard the squeaky.
What was that in there?
Oh, they're washing their
pads.
Can we close the door, maybe?
Yeah, go ahead, yeah. My hearing is fine, generally, but
Well, no, I've heard like certain like pitch noises, like it
People
depends
can't.
on like people's age, whether they can hear.
Yeah.
Yeah.
They're closing the door for the squeaky car.
Like, you just gotta like push it, like don't turn it off, just be aggressive.
There we go. So hopefully that helps, but every once in a while, maybe a speaker or something would start giving out, and then we'd get a squeal. But I could hear it a little bit, but So anyway, the other thing that people do is, these are the two principal components in this example. So you could regress on those components, but that's the idea. In this particular example, it's supposed to be this classic example, nothing works as well as picking one particular variables like GNP or year or population size and regressing on those. Those are so highly correlated with the employment numbers that those by themselves, without the noise of armed forces and some other things, does the best. Right? So, so in principle, the general idea, these principal components do reduce it to a couple of dimensions, which suggests how you might use variables, but still sometimes looking at individual ones does a little bit better. So I'm always interested in trying some of these examples that are supposed to be classic ones and trying to figure out why these are the ones that are used. The principal components is affected by scale. So in our long lead data, say the first 3 rows of it, there are quite different scales between some values. Right? The DNP deflator doesn't vary, well it does, right? But some of these other things are going in the tens or hundreds, and others are just changing 1 unit at a time. So there is a difference in scale of these variables, and so maybe that's affecting things. So you might want to look into it a little bit. How are other things related? I wanted to look at some of these other data sets. So one data set that this has been used on are things like data on different states. So this is 1970. This help file is here. Right. So this is violent crime in 1973 in the different states. And these are the plots of 4 variables that are on the data set. Murder, assault, and rape are the crime variables, and just urban population. And these are somewhat correlated with one another. There's not too many variables, so you might not actually need to really reduce it in any time. If you do this variance inflation factor on this data set, you get very modest values. So this would suggest that the x's are not highly correlated for predicting one of these, and therefore principal components probably is not needed, right, to try and find factors. The first case study has another number of metal rods, and they're looking at, what they're doing. They're looking at the magnetism rating across different spaces on a rod, and so there's 11 measurements on each rod. And so if the entire thing is magnetic, all 11 of them are going to go up together, and if it's not magnetized, then they're going to go, be smaller. So these 11 are really pretty highly correlated. It's a designed experiment, so actually current is not really a outcome variable. You can set the current to different levels going through this machine. There's 2 configurations. There's 4 different materials. But the values L1 through L11 are highly correlated, and when you do the variance inflation factors for those, you get things that are in the hundreds or thousands. Right? So if you looked at the plots of those, the pairs, pairs 1 through 5, I probably picked this just to get to 5 of them. The L values are highly correlated. If you try to use all 11 measurements to predict something, it's just going to fall apart, right? It's going to be standard errors that are huge when you know that there's high correlations, and it's not going to work so well. So it might be a case where we would use principal components to reduce the dimension from 11 down to some number. The second case study has measurements. We can talk about what they are. But their scores 1 through 5 for a husband and a wife about is there a passionate relationship in the passionate love toward the spouse. And this is like a husband rating of the wife and the wife rating of the husband. And so if you look at those across here. Generally, they're similar scores. They're mostly on this diagonal where the pairs are giving similar ratings, but there's some variability about that. Right? You could look at other, there's passion and compassion is the C, and so that you can't see, but most are 4s and 5s. They're a little bit less, 4, 5, 5, 4, 4. So this one's a little bit less. So they're not highly correlated. There'd actually be 28 different pairs of variables you could look at. You can't really plot them very well because of the 1 to 5 scale, but you can compute these variance inflation factors to see how correlated these things are. Now the couple really is just the number of the couple, like 1 to 32. So you would never really regress on that, but you can kind of trick the software into doing the variance inflation factors on all the x's, on all these different variables. And those are not too high. One of them gets a little bit higher because it's kind of correlated with some of the others, but it's not too bad. This USA arrests, right? If you want to look at, so there's 4 variables on that. Let's go back to that, right, of these. Now, is there any kind of overall factor underlying these things? Is there some dimension that describes the patterns among these many variables? So if you use principal components, you can specify it a couple different ways. And it says that there are, the standard deviations of these coefficients are the first 2 are a little bit larger, the second 2 a little bit smaller, and the cumulative proportion of the variance of these 4 things explained by these is there's kind of a first principal component that's about 62%, about 2/3 of all the variability, and a little bit more for the second one, and a little bit more for the third one, but it looks like there's a little bit of redundancy. So the loadings that come out of this one, all of these are going in the same direction. They happen to be negative, it's a numerical solution, so. But this, if you weighted all the values by that, it would be kind of like an average, right? The second one, though, has some negative and some positive coefficients. And there's a big negative coefficient on urban population, right? And then some positive coefficients on those. So there's kind of a difference between population size and rate. So kind of a contrast there. This one looks like an average, and this one looks like it contrasts, well, just rate is positive, and those others are negative. So again, it's a kind of contrast in that dimension. Maybe that is something that would be worth looking at. When people look at these things, you can look at averages, right? This is the kind of the center and the scale. There's things for describing those principal components. What I wanted to look instead is at the plots of the scores. So this one had 4 variables, right? So these principal components are supposed to be uncorrelated with each other, right? And so the first and the second, they don't have much pattern. The first and the third, the second and the third, and so on. It does find variables that don't really have much pattern to each other. Right, so if you put the first and second, or the first and the third, or whatever, into a regression, or something that looks pretty much like them, like an average or a difference, then it's not going to have X variables that are correlated. So you shouldn't have that problem of it trading off. If you look at pairs, right, a little bit closer, here's the USA scores 1, USA scores 2, the principal component scores. One thing you can notice, look at these plots, is that as you go deeper into it, further down, the standard deviation tends to get smaller, right? But the variability is biggest for these first ones, and then it gets less. So the first versus second, the variability is bigger in the first dimension. If you do the second versus the third, again, it's getting smaller, and the third versus fourth, it's getting smaller again. This might be also another case where, depending on whether you do it on the correlation scale, standardized things, or you do it on the original scale, there is some difference in the units of measurement, so that will have some impact on how variability gets measured. So let's think about doing a couple of these things, right? In the first case study, well, you can't really see that, can you? If you do the first, say, 5 of these, there's these five different, they're highly correlated. And this is an experiment. And so in this experiment, ultimately what we can think about doing is predicting the magnetism score of one of these outcomes, like the first part of the bar, how magnetized is it, as a function of the current, the configuration of the machine, and then the type of material. Well, those things are all actually factors, even though they're scored as numbers in the data set. And so we could think about regressing L1 on these different factors. Right? And it ends up that this really is not significant, this design experiment, across these different voltages that are put in, the currents that are put in, and the different materials and the configuration. It does not seem to have any significant differences at all. Right? But that's L1, right? That's just one measurement. Right? One measurement, maybe there's a lot of noise in that one measurement. We have L of them, we have 11 of them. So maybe we should do something to try to capture more of the systematic pattern. The idea, I guess, if we're using principal components of this, would be to see is there some dimension. You can do this for the first one, the second one, you can do this for all these different components. That seems a little bit, searching for something. But is there a good measurement of the variability in the L, the magnetism that's there? If you do principal components on this thing, here's how you could specify it. The first principal component actually takes up about 96% of the variability of all these 11 measurements, right? Which suggests that whatever that first component is, it's most of the variability. Right? So we're going to use that as an outcome, something to predict. So if you can express most of the total variability in all the y's through just one measurement instead of 11, maybe that would be the way to go for the regression. Looking at the components that are on there, they're all kind of the same coefficient. They turn out to be negative in the computations. But they're all about the same. Right? So if you took a weighted average of these things, they're kind of the same scale. Measurements are not so much different from each other. And this would suggest to take about an average of those. Right? It's easy to tell somebody to take an average of all your 11 measurements. It's kind of difficult to tell them to use these particular coefficients, but it's pretty close to an average. So principal components would suggest we take an average. What do the other ones look like? The ones that here are blank are practically zero, right? So they're not reported. But it looks like there's a bunch that are negative here and a bunch that are positive. Right? This is a bar of metal with 11 measurements along it. Right? So it's kind of doing a contrast between the beginning and the end. Right? Is there a difference between the beginning and end? What does the next one look like? Well, there's kind of the beginning and this kind of middle part. Is there a difference between the beginning, the magnetism in the beginning and middle? Right? So it's kind of helping us break this up. This fourth one, is positive here and mostly positive here. Well, it's a little more chaotic. It's kind of positive, negative, positive, negative, positive. It's almost like, is there kind of a sign? Is there kind of a curve going up and down across that? I know that's reaching a little bit. That's a little bit less strong to see. But the first one's really kind of an average, and the next two might be kind of contrast between parts of this bar. Here's the plots of the principal components. It turns out that there's a few kind of extreme points out there that are sticking out. So they're kind of a clustering. Remember this designed experiment, so we could probably do some plots to figure out where those points are a little bit more, are there some of the bars that are particularly different than the others. So you could learn a little bit there. And if you regress this principal component score on the other factors, well, again, the R-squared goes up a little bit, but still, overwhelmingly, it's not significant. Whether you look at L1 by itself, or this average across the bar, it does not seem related. So principal components seems effective in telling us we want to take an average or maybe a contrast of things, but the experiment doesn't really, I think, show any significant impacts of the bars becoming magnetized in the machine or anything like that. So I think it captures something, but it the experiment didn't really do too much. So here's a little bit more about this this second case study example. Right? So this had spouses, male, female spouse, husband and wife, and basically had 4 questions for each person. So what level of passionate love you feel for your spouse. The data sets, you can get that information if you do the help of the, right. If you do the library of the sleuth thing here, there's help files for each of these data sets. I haven't done too much with that, but if you're looking at a particular data set in the book and you type help of it, it will tell you more about it. So that's nice. Going back to where we were here in terms of this example, there's passionate love. So the husband rates how the spouse feels, then how he feels, and then they do that about compassion as well, right? And so then you get 8 variables, right? How HP is how the husband feels to the spouse. So that if H is here, it's the husband's feelings or the wife's feelings. And then this is the rating, the passionate love the husband perceived to have for him. So this is the passion, so it goes the other way. So there's the husband's ratings, the wife's ratings, to and from passion, compassion in there. 8 variables. And in social sciences, sometimes there's the idea that there's an underlying factor, right? Maybe there's a passion factor or a compassion factor or a to or from. There's different types of factors like that. If you fit the principal components for this, the standard deviations of the principal components don't drop off so fast. That's related to the proportion of variance. I'll just do that and HP. So I don't have that. Just the data is not attached. This is the attach case 1702. Okay. Principal, that is there. And so the second principal component is the standard deviations. And then if I look at the loadings for that, we get those. I think I want summary of that to see the. So in this case, the first principal component only is about 1/3 of the variability, right? And then the second and the third and the fourth. It doesn't drop off so fast as in some of those other examples. Right? The economic example, you're up to 90% right away, right? And the L1, L2, the first one was also really high. But this one, in this social science one, there's more factors that seem at play here. So it's harder to identify just, if there was only one that came through as dominant, maybe that's strength of relationship. But passion, compassion, to, from, husband, wife, there's all these different things. And so it does, in this social science one, kind of a richer, more complex framework for thinking about what's going on. So you might not be able to divide it up quite as much. One thing you could do with this, it's not really a kind of a regression output to judge, to predict. You can just use this for dividing up the data. In this second example, they really use this thing called canonical correlation. So if you had a linear combination of the husband's measurements and a linear combination of the wife's measurements, are those related to each other? Right? Is there some group of variables? And so they kind of look at that thing. But one thing you could do with principal components, the first loadings, right? Which ones are involved here? There's kind of a few that are positive and a few are negative. It's a little bit more complex to think about, and I don't know that I have good interpretation. One thing you could do is plot the points. Here, plot the scores and just look where people are. Right? So if you put the text in there, these are the numbers corresponding to certain couples, right? Some couples are very high in this first one, very low over here, and so on. Right? These are the first two principal components. So it's 2 dimensions instead of 8. And so some couples stand out. Right? If there were big gaps in separation, maybe you get clusters, but it looks kind of more of a continuous map. It's hard to say that there's a group over here and a group over here. It's just kind of all over the place, which is kind of interesting that there can be gradations. You know, some social science questions are about clustering so that there are distinct groups. I think it'd be hard to call them distinct groups. Some research proceeds by taking extremes, like we want to follow up with people up here and people down here to see if there's differences between the extremes. Sometimes that cut is made, it kind of artificially makes groups. This occurs a lot in research. If you look at, 1 and 28 are over here, and 25 and 12 are over here. So if you look at those particular people, here's their scores, right? Everything's scored 1 to 5. Right? How do 1 and 28 differ from 25 and 12? Well, HP is lower for this group, right? WP, a little bit, not too much difference. There's a little difference here, but mostly it's these two numbers are different. CW, there's a little different. So it's not grossly different in these, it's just kind of subtle. But they do get a lower ratings, particularly in terms of the husband's perception there and something else. So that's it, that's all that, that's kind of a subtle difference, but that's what it's picking up as part of a pattern. You could look at this dimension too. 11, 18 are up here, 10 and 29 are down here. How do they differ? Well, the weighting factors on this one, HC was a little bit bigger. I'm just looking at the size of this coefficient here. CW was a little bit bigger. And then if you look at HC here, right, these two were 3s, and these two were 5s. So that's kind of grading that. CW, again, 5s versus 3s. PH was another one that had some rating, so it's 5s versus 4s. So there's kind of a lower, higher separation in those dimensions. If you had larger samples of this, other factors, maybe this would generate some hypotheses for you about underlying things that are important. If you're interested more about principal components, I put some resources online, a few articles in there that you could look at. One of these I think is pretty interesting to think about. At UCLA, they have a statistical consulting site online. Right? This is for digital research. It used to be called, I don't know, it used to have a different name. But anyway, it's there. And then there, about software, there's things on R, Stata, SAS, SPSS. M+ is something for hierarchical models and others, but under R, there's a few modules for learning things about it. And there was this particular one, if I can, I have to get that part. Does that come up with anything? It has a site here, I guess like it's changed. Choosing the correct statistical test in SAS data, SPSSR. So it gives a little chart that does these different things about different things. And let's see, trying to find how to. Anyway, when I had it before, let me close up, let me just try to open it in tab. this thing, what statistical analysis should I use? And so it talks about this little data set here that has some things in it. And then it says what type of things might you do for a one sample test with it, or a median test, a binomial test, 2 independent samples, some other things, one-way ANOVA example could be used with this data. And so, and then down at the end, it's, there's some things with regression too. But then there's something with factor analysis, which is like principal components, and this thing, what is this thing? A lot of coefficients there. But this and canonical correlation, like in our book. So it has some examples in there of thinking about different things. That's one thing that's kind of interesting to look at. The other ones are focused, the other articles are focused on doing principal components in our, how different software options for doing that. And then an example is included with that. And so this is a survey data. It has race, social, economic status, and so on. But then scores on reading, writing, math, science, and social studies. And so the values it has, reading, writing, math, science, social studies, is a number of dimensions. And if you do a pairs plot of those, you see some correlations. Reading, writing, math, science, social studies, right? Kind of on the same scale for most variables. So is there an underlying factor that's, that you might be interested in? And you might be just interested in dividing that up, but maybe you're looking at predicting scores. You could consider predicting reading scores or predicting writing scores or something like that. But if there's kind of a dominant kind of intellectual achievement factor under there, you might try to predict that. Is that related to expenditures? Is that related to social economic status and other things? Right? So instead of predicting each of these, is there some good factor that would be worthwhile to study? If you do principal components on this data set, the first principal component has about 2/3 of the variability. There's a couple others, 2, 3, 4, that have pieces of it. But the first one's about that. And the first one, again, all the coefficients are going the same direction. And it looks like kind of an average if you think about that, right? The second one seems to be a contrast between math, science, and social studies. Their achievement there. The third one looks like a contrast between writing and reading, right? I was at a parent-teacher conference yesterday, my daughter in middle school, and so an issue was, there's writing and there's reading, and you can have achievement levels different in 2 different things. There's 2 different skills there. So this one's kind of interesting to me that because of recent discussions and so on. But the first one's kind of maybe this could be interpreted as kind of an overall achievement, weighting together these different categories in a way. Not all educational evaluations would have all of these categories, right? So that's kind of interesting that it actually has social studies in there that's maybe not, and reading and writing separate. It's kind of interesting that's there. So you might just look at that and create that outcome and then say, is that related to race, school type, program, and so on. This data set's on the UCLA site and still can be read in, so it's something else that might be interesting. One example to kind of finish up is in the book. There's one exercise and related to religions. They had a number of Protestant denominations, and a bunch of experts rated how distinct these religions were from others, right? In terms of having their individuals in the religion do certain things, dress differently, attend activities, be more strictly associated with the church, particular beliefs, particular practices to make them distinct from general culture, right? And they had predictive variables: attending church, non-church activities, percent that identify themselves as strongly affiliated with religion, and then annual income. And if you do a regression of these, maybe do pairs to see what these things look like. Pairs of the first column is the religion name. So they're distinct versus attendance. So there's some pretty strong, good relationships to predict that. Some of the variables, like non-church activities and percent strong, there's some correlations there, maybe not super strong. If you run that regression, some reason, why didn't I like that? Attach. Then I can run that. I get this R squared, and some things like attending church, right, percent of time that you attend church, to predict distinctness, doesn't get a significant regression coefficient. Right? And it's probably because, other things, attend is kind of correlated with these other things to a degree. So with all of them as predictors, some of these things that you would clearly think should be significant don't really work out. There's also a much different scale, so I standardized some of these things to put them all on kind of a similar scale. And if you do the regression again, you still get the same p-values, same R squared, because everything's just a linear transformation. But now the coefficients aren't, before they were pretty crazy small, because it was thousands of income down to percentages and so on. These are easier to look, but doesn't change any of the significant story. Variance inflation factors were not so high, but so that maybe there's not that too much of a problem there, but it still kind of shows up. If you do the principal components, it looks like you get a couple things. The first principal component looks like a combination of percent of time attending church and percent strongly identifying the religion, right? So kind of their behavior and their statements together. The second one is kind of a contrast between those two things, which is kind of interesting. And the third is something else. So when I try to do a stepwise selection, those start with all the 4 variables. Maybe I go down to just an intercept all the way up to second order interactions and things. It ended up with a model that essentially had the number of non-church activities in there, and then the percentage. Let me just double check this. Things are off. Attend. Okay. Something's okay, where would that be? 4, 6. This, anyway, I don't know, something kind of looks a little bit off with that, perhaps. But anyway, yeah, so I think that the non-church was supposed to be in there or something like that. It's kind of like non-church, there's a couple variables that are in there and these others. So maybe something a little bit off in this last bit of output. But anyway, it ended up with a couple variables in there. And so they're kind of related. Not using all the variables, some using not significant. And so that's something about principal components. Right? Homework. I'll pick up the homework and get your comments back on that. And have a good weekend.